Hello everyone. In this video we're going to learn the difference between speed and velocity. Our objectives are understand the difference between speed and velocity, know how to calculate the speed and velocity of a moving object, and know how to make speed and velocity graphs. This is the first part series for chapter 2 on kinematics and motion in one dimension. Let's start off with speed because that's what we use in everyday language. When you're talking about how fast you're going in your car, you're probably talking about the speed of your car. So speed is simply going to be the distance divided by the time. Sometimes we put a bar above that because it's average speed. Make sure you always have your units, could be in miles per hour. Now the key thing with speed is it doesn't matter what direction you're going in. It's a scalar. You're going to hear that term a lot in physics. Scalars only have magnitude, they don't have direction. So if you're driving to the north, south, east, or west, it doesn't matter. It's always positive, and that's going to be your speed. So we'll give a formula something like this. Speed is going to be your d over t. Okay? And that's how you'd see it written in most textbooks for the speed of an object. Okay? Now the velocity is related to speed, but it's a little bit different. Instead of using distance, we're going to use displacement. Okay? And velocity is a vector. What that means is it has magnitude and direction. So your velocity of your object is going to be your displacement, which is your final position, minus your initial position. That's what the little subscripts F and I stand for, divided by your final time. Sorry, let me get rid of that here. Not quite there. So your final time minus your initial time. Okay? And we'll shorten that into, that's what I was drawing down there. This delta symbol is the Greek letter change in. It's always your final minus your initial. So this is how you would see your velocity formula. Change in position divided by change in time. And that's how we would define velocity. Now, what that means is sometimes you can have a positive velocity or a negative velocity. Usually going to the right or to the east we'll call positive. Going to the left or west we'll call negative. Up is usually defined as positive, and down is usually defined as negative. Okay? Forward would be positive, backward would be negative. Now, just because you have a negative velocity doesn't mean you're slowing down necessarily. It just simply means you're heading to the left or you're heading down. So velocity is a vector because it gives you both magnitude and direction. Okay? So let's look at an example here for how to make a graph. On this example here, we're going to do a speed graph of an object that looks like after 1 hour they've gone 10 miles. So someone who's maybe jogging, and we're going to make a little graph here for this object here. So 1 hour 10 miles, and then 20 miles, 30, 40, 50. It's going to look something like this. So you get the idea. You want to do these with a ruler or on Excel so you do a nice straight line, much better than what I'm trying to do here on the screen. Okay. Now, a couple key things when we do a motion graph, this is very important. You always want to put the time on the x-axis. It's very important. So in this time, we have the time in hours on the x-axis and our distance on the y-axis. And by doing that, we can look at the slope of this object, which is our rise over our run, the distance over the time. The slope of this object is going to be the speed. And you remember back in algebra, slope is going to be y2 minus y1 over x2 minus x1. And that's going to get you your slope. And when you do it for this problem, you're going to get 40 over 4. That's going to be 10 miles per hour. Okay? That's your average slope. That's your average speed for that runner in this particular problem. Okay? Moving on to this example here, a little more detailed. We have an object that starts off going 10, 20, 30, 40, 50, and then they turn around and go back to 40, and they end up at the 30 meter mark, and the time is increasing by 4-second intervals. So first of all, let's make a kind of a motion graph to show what this object is actually doing here. This is someone who's going to be doing wind sprints. Okay, so they start off here, they go all the way to the 50 meter mark, and then they turn around and go back to the 30 and they stop right there. And that kind of describes the motion of that object here. So if we're going to make a velocity graph, it's going to look like this. After 4 seconds, they're at the 10, And then after 8 seconds, they're at the 20. 12 seconds, they're at the 30. And you kind of get the idea here, 40. And then they're at the 50 mark at the 20 seconds. So this is the maximum displacement they go right there. And then they abruptly turn around and then they head back. And this is where they end up. So you want to make a nice graph of this thing, hopefully better than what I'm trying to do here. I'm just using dots to try to get a straight line here, because I can't draw a straight line on the computer very well, but you get the idea. And then it's going to go back like this. So that describes the motion of this object here. And if you look at the graph here, you've gone, let's see here, 20 meters after that. So the total time here is going to be, the slope of this object here is going to be rise over run, which is going to be 50 over 20 is 2.5. So this is a positive 2.5 meters per second. That's their velocity as they're moving away. And then if we do a slope over here, it's the same magnitude, but it's just negative 2.5 meters per second. Okay? So this is a velocity graph, a little bit different than a speed graph. Now, if they were to get to the 50 meter mark, and let's say they were a little gas and they slowed down, the second half of their journey would look something like this. It would have a more gentle slope. It would still be negative, but it wouldn't be that magnitude there. Let's say they got to the 50 meter mark and they wanted to go really fast back to the 30 meter mark. It would have a steeper slope. It would look something like that. Okay? So the slope tells you how fast you're going. The positive or negative tells you the direction. So I hope that clears up the difference there. All right. So let's do a calculation here. What's the speed of that object? Okay? It's going to be the total distance that it traveled. So it went to the 50, back to the 30. That's a total of 70 meters. And what was the total time that it did that in? So if we go back here, so it did 70 meters. I have to go back. So it did 70 meters in 28 seconds. And when you divide that out, you end up with 2.5 meters per second. That's your average speed. What about our velocity? X final minus X initial divided by T final minus T initial. Your time's still going to be the same. It's still going to be 28 seconds. Your final position, you're at the 30 meter mark. Your initial position was at the 0. So you're going to be 30 divided by 28, which comes out to be, I believe it's about 1.1. So you're going to be about 1.1 meters per second. Let me just double check that. Yeah, so the average is about 1.1 meters per second. So your speed and your velocity in this problem are not the same. It's because you return back. So your total displacement is less. So that's why you're going a little bit slower in your velocity. Okay? All right, let's try another problem here. An airplane flies 600 kilometers away from its base at 200 kilometers per hour. Then it flies back to its base at 300 kilometers per hour. What is the plane's average speed? What is the plane's average velocity? And make a speed and velocity graph. I'd like you to pause the video for a minute here and try to solve these A, B, and C, and then come back and see how you did on this. All right, so I'm going to start off with the diagram here. It always helps to draw a diagram when you're doing a physics problem. So you go away and you go a total distance of 600 kilometers. And here's your airplane. And the velocity that you're going, or the speed that you're going as you're going away, is 200 kilometers per hour. Then you hit to this 600 kilometer mark, and then you fly back, but you return at a much faster speed, probably because of a headwind in one direction, at 300 kilometers per hour. Okay? And they want to know the plane's average speed and the plane's average velocity. So let's do that calculation here. So its speed is going to be its distance divided by its time, We know the speed, we know the distance, we don't know the time. So I'm going to rearrange this formula here so that t is by itself. So this formula becomes t is going to be distance divided by speed. Okay? So on the journey away, it's 600 kilometers, and the speed is 200 kilometers per hour. Okay? When you divide that out, you get 3 hours. That's how long it takes it to go away. When it returns back, same distance, 600 kilometers, but now you're going 300 kilometers per hour. Okay? And when you divide that out, you get 2 hours. The total time for the trip is 5 hours. So now when we get our speed, it's our total distance, the 600 plus the 600, it's going to be the 1200 kilometers divided by the total time, which is 5 hours. Okay? And when we divide all that out, we get 240 kilometers per hour. Now, a lot of people just jump to the conclusion and then say, oh, its average speed is 250. But you can't do that because it spends less time at a higher speed, which changes it a little bit. So it's not split down the middle. This is an example in physics. Sometimes you have to do the math and don't just rely on common sense. Okay? What about the velocity? Okay? Our average velocity, we're going to take our final position minus our initial position divided by our total time, t final minus t initial. So, well, we ended up back at the base, so we're going to call that 0. And we started at the base. And it doesn't matter how much time you have there. When you divide it out, you're going to get 0 meters per second. There you go. So your average velocity for that trip, because your displacement is 0. There's a perfect example of the difference between distance and displacement. So your velocity is 0 because your displacement is 0. Okay? What about the motion graphs? How's that going to look on the motion? Well, for the first 3 hours, it took it to go 600 kilometers. So it's something like this. So that's the journey away from the base. Okay? And then it takes it 2 hours to return back. So it goes another 600 kilometers in 2 hours. So that's going to be something like this. So this is the speed graph for the airplane. 2 different slopes here. This has a slope of 300 kilometers per hour, and that has a slope of 200 kilometers per hour. They're both positive. So that's the speed graph for the plane in its journey. What about the velocity graph? Well, in 3 hours it goes 600 kilometers. So the first part of this is going to look just like what we did over here. So 3 hours, 600 kilometers. Going to look just like the speed graph here. But this is where it's different. When it returns back, it goes back to the 0 point in 2 hours. So this is the return journey. It has a negative slope. This is a positive 200. This is a negative 300. It's going faster on the way back. So same problem, but the velocity graph looks very different than the speed graph. So I hope that clears up the difference between speed and velocity. We use them both in physics all the time. A couple key factors: always make sure your time is on your x-axis and whatever you're graphing is on your y-axis, and the slope of your speed is going to be the slope of distance over time is going to be your speed. So I hope that clears things up, and we will call it with that, and we will work some practice problems in class going over these specific examples.